Alright, so we're going to go into some mathematical vignettes of the study of stellarator mathematics. This will involve us talking about ideas from three different fields of math, from partial differential equations, from dynamical systems, and from differential geometry. I'm going to start by telling you a little bit about the MHD equilibrium equations, then we'll move on to talking about axisymmetric containment, and finally I'll tell you a little bit about how differential forms are used to understand quasisymmetry. Let's start with the MHD equations. So the MHD equations, without taking the equilibrium right away, are going to be given by four equations here. Before we had more, but I've simplified them out a little bit. The first two equations are from the Navier-Stokes equations. These tell you how a fluid flows. And the third and fourth equation are from Maxwell's equation. They tell you how, when you have charged particles moving, how does the magnetic field get produced? Okay, so in the first equation, we have the acceleration, which I've kind of canceled at the mass here, but mass times acceleration is equal to the forces. This is just Newton's law. One of our forces is the pressure force from a flowing fluid, and the other one is the magnetic and electric force, the Lorentz force that you experience if you're a charged particle moving in a magnetic field. We're also demanding here that our plasma be incompressible, so you can't squish it or stretch it. We don't want to demand this if we have a gas, but in this case, we're just going to take incompressibility for making our life a little bit easier. Then we have the magnetic field. The magnetic field changes according to the velocity of the particles and the magnetic field itself. We take their cross product and then take the curl. And then finally we have Gauss's law that says that a magnetic field always has zero divergence. Sometimes we'll see the current pop up. That's just going to be the curl of the magnetic field. Okay, now let's take the equilibrium equations. This is when the plasma isn't moving, it's nice and stable, and the magnetic field isn't changing. So when we do that, the left-hand side of this equation is going to go away. The incompressibility equation will be 0 equals 0. From this equation, we'll have this side as 0, and we'll have u being 0 makes this side 0. And so all that's left over is Gauss's law, that divergence of B is 0, and the right-hand side of the first equation, which says that J cross B is equal to grad P. Okay, so we've got two equations now, and things are a lot simpler. Let's try to understand some properties of this equation. For example, what happens if we dot the first equation with either B or J? If you take the dot product of the first equation with B, then what you find is that B dot grad P is equal to B dot, well, J cross B. But J cross B is a vector that's perpendicular to both J and B. So the dot product with B is 0. So we end up finding that the directional derivative of P in the direction of the magnetic field is 0. Similarly, the directional derivative of P in the direction of the current is also 0. This is useful because we can now study magnetic field lines. A magnetic field line is a curve that follows the magnetic field. So at each point, its tangent vector is just going to be the same as the value of the vector field at that point. This is a differential equation that tells you how to get the magnetic field lines from the magnetic field vector field itself. Now let's figure out what the pressure is along a magnetic field line. If we take P at gamma of t, 1 point on the magnetic field line, and we take the derivative as time increases, then we can use the chain rule. We'll get gamma prime times the gradient of the pressure. We have to use a dot product because these are both vectors. But we know that gamma prime is just B. And so that tells us that since we know that B dot grad P equals 0, that the derivative of P of gamma of t is 0. Okay, well, if the derivative of P of gamma of t is 0, that means that P of gamma of t must be constant. It's just a constant function. So P is constant along magnetic field lines. And it's also constant along current lines. This tells us that J and B are going to lie along the level sets of P. If you take a surface that's defined as a place where P is constant, your magnetic field and your current must lie on those surfaces. This gives us those flux surfaces that we talked about before. This is all great if your pressure is not constant, if it's high in the middle and it goes to zero as you go towards the walls, which kind of makes sense if you're compressing a gas inside of the space. But we can also study the situation where the pressure is constant. When the pressure is constant through the device, we no longer have that its level sets are nice surfaces, and so we don't have any guarantee of flux surfaces for J and B. But we do end up with some other interesting mathematical theory. When J cross B equals 0, that's what happens when the pressure is constant. That means that J and B are parallel vectors, because the cross product of two parallel vectors is 0. Okay, if B is parallel to curl of B, then that means that curl of B has to be equal to B times some constant. Okay, at each point this constant could be different, so we need some function lambda of x. That's the proportionality between B and its curl. When this happens, we call this vector field B a Beltrami field. Beltrami fields are important in fluid dynamics and in plasma physics, but they're kind of hard to study. Let's study the simplest case. For example, when lambda is just equal to a constant. In this case, our vector field is proportional to its curl. We can think of this as saying that Beltrami fields with lambda being constant are the eigenvectors of the curl operator. Okay, so we have a vector field, so that when you take its curl, you just get the vector field back times a constant. What can we say about such vector fields? Let's apply this twice. So we'll take the curl of B. Well, when we apply curl once, we get lambda, and then when we apply curl again, we get lambda squared. So the curl of B is lambda squared times B. Now we can take a little bit of a detour. The Laplacian is an important operator in a lot of places in partial differential equations and physics. What does it mean? If you take the Laplacian of a function, it just means that you take the second derivative in x, in y, and in z, and you add them all together. In this case, since B is a vector, we just take the derivatives in each component and add together. Why am I bringing up the Laplacian out of nowhere? Because the Laplacian for a three-dimensional vector is actually related to the curl of the curl. The Laplacian is equal to the grad of the divergence of a vector field minus the curl of that vector field. Okay, this is kind of nasty to figure out why it's true. I highly recommend, if you want a good multivariable calculus exercise, try computing this out and seeing why it works. Okay, start on the right, write down this formula, write everything out, and see why you get the Laplacian at the end. But for now, we won't do that. We'll accept this as given. And we know that for our magnetic field, the divergence is 0, and the curl is lambda squared times B. So we end up getting that the Laplacian of B is equal to minus lambda squared times B. This is an important equation called the Helmholtz equation. It's the eigenvalue equation for the Laplacian. The Helmholtz equation is important in a lot of places in physics, for example in quantum mechanics, and even if you want to answer the following question: hearing the shape of a drum. So if I'm in a separate room and you have a weirdly shaped drum, and you strike it with a mallet, if I record the noise that it makes, and I feed that into a computer and I break it down and analyze it, is it possible for me to figure out what shape the drum you hit was? It turns out that the answer is really close to yes. There are counterexamples of two shapes that have the same set of resonant frequencies when you strike them, but they're really rare, really difficult to figure out. Most of the time, it uniquely identifies what the shape of the drum was. And the core equation behind this is the Helmholtz equation. Each of these functions on the circular sort of drum are different solutions of the Helmholtz equation for different lambdas. on the top right, you see a weirder shape, where the solutions end up having different harmonics, different frequencies of vibration. So it turns out that plasma physics is related to all kinds of different areas of math, as long as you work the equations and massage them into a nice form. This is just one way to go with things. You can also understand these PDEs by understanding the waves that exist within them, by understanding conserved quantities that they have, like energy and helicity. You can understand their analysis. When are their solutions? What's their stability? And so on. These are all kinds of things that I'm interested in studying, but they're a little too difficult for the talk today. So feel free to come and talk to me if you're curious to learn more. But for now, let's move on to talking about a different vignette. We're going to talk a little bit about dynamical systems. In particular, why is it true that a tokamak perfectly contains a plasma? So let's start off with an equilibrium, J cross B equals grad P. How does a charged particle actually move inside of this magnetic field? We know that it tries to follow the magnetic field lines, and that it also experiences drifts off of those magnetic field lines. We also know that it tries to move not just directly along the magnetic field lines, but in gyro orbits that are tightly wound around the magnetic field. Let's figure out why all this happens. Okay, so first of all, we know that the divergence of B is 0, and this lets us define something called a vector potential. This is going to be a useful tool for understanding the dynamics. The vector potential A is kind of like the integral of the magnetic field. It's a function, it's a vector field, so that when you take its curl, you get B back. Okay, I won't tell you why there's such a thing as the vector potential, but you might have heard of potential functions for curl-free vector fields in the past. This is a similar idea. And using A, we can define something called the Lagrangian for a particle moving in a magnetic field. The Lagrangian takes in two variables, the position of the particle and its velocity. And it spits out something that's kind of like the difference between the kinetic and potential energies of the particle. M over 2 times v squared plus q, the charge of the particle, times AR, A was the vector potential, dotted with v, the velocity of the particle. Remember that A is a function of positions, this is just A at the particle's position. Well, this Lagrangian is useful because it actually lets us determine the motion of a particle inside of this magnetic field. It lets us do that through a type of math called calculus of variations. This is a really nice type of math, and I'm not going to go through the details of why this works, but what I think is really fun is to go and look at this on your own and see how it works for some simpler cases. For now, let's talk about the Lagrangian for a magnetic field. So the Euler-Lagrange equations will tell us how our particle moves. They come from using the Lagrangian in something called the action. If you give me a particle path r of t and its velocity r prime of t, we can feed those into the Lagrangian, take the integral over the whole particle path, and that's something we call the action of the particle, or the action of the path. If we find critical points of the action function, taking the derivative and setting that equal to 0, for example, the minimizers or the maximizers, then we're able to find the actual path of motion of the particle as it moves. So if you try to take the critical points of the Lagrangian, you end up finding an equation that tells you what the paths of motion should follow. It's called the Euler-Lagrange equations. In this case, it looks like d by dt of dl dv at r and r prime, which were r of t and r prime of t. And we need that to be equal to dl by dr of r and r prime. Okay, this is pretty complicated, but let's see how it manifests for our case. First things first, we need to find dl dv. So L, right here, has a v squared term, and it also has a constant times v term. So when we take dl dv, we get mv plus q times a of r. Now we can go ahead and plug in r and r prime. We've already got r here, but v needs to become r prime. And then when we do that, we can take the time derivative. When we take the time derivative of r prime, we get r double prime. And when we take the time derivative of a of r of t, we need to use the chain rule. We'll get r prime coming out, and that needs to be multiplied by the derivative of a, which will be the gradient of a evaluated at r. Okay, so this was the left-hand side of our Euler-Lagrange equation. Now let's do the right-hand side. This is dl dr. Going back, r doesn't appear in the first term, but it does appear in the second term. We need to take the gradient of a of r dot v. Okay, this doesn't look so bad, right? There should be a nice product rule for the gradient of a dot product. Actually, it turns out that the product rule is really nasty. It's pretty terrible. It has 4 terms. Some of them involve dot products, and some of them involve curls and cross products. But for us, things are not going to be so bad. Okay, let's look at each term. If you're curious in figuring this out, they have 2 different options. You could either try to compute this sort of product rule yourself, which I highly recommend. It's a good exercise to do for multivariable calculus. Or you could go to the Wikipedia page of vector calculus identities, which is my best friend. It's also why I know that identity for the Laplacian being equal to grad div minus curl curl. That's where I got this guy from. So the first term here is a of r dotted with the gradient in r of v. Well, v and r are different variables, so v doesn't depend on r at all, so this is just 0. The next term is v dot the gradient in r of a. This term sticks around. Next, we have a of r cross with the curl of v. Once again, v doesn't depend on r, so this is just 0. And our final term is v cross the curl of a. That term's not so bad because we know that the curl of a is supposed to be b, the magnetic field. Okay, so we're left with q times r prime. I'm substituting r prime in for v now. R prime dot grad of a plus q times r prime cross b. But on the left-hand side of our equation, we also had a q times r prime dot grad a. So that's going to cancel out on the left and on the right. And we're just left with mr double prime is equal to q times r prime cross b of r. This is just Newton's law for a particle moving in a magnetic field. On the left, we have ma, and on the right, we have the force. This is the Lorentz force of a particle moving in a magnetic field. So our Lagrangian was the right Lagrangian for the job. It ends up giving us the right Newtonian dynamics. But our Lagrangian is more powerful than that, because now we can make use of symmetry. Let's see how Noether's theorem works. Suppose that B is axisymmetric. If B is axisymmetric, well, we need to write things in cylindrical coordinates. In r, phi, and z coordinates, remember that r is your distance from the z-axis, z is how far up the z-axis you are, and phi is the angle that you make as you sweep around. When B is axisymmetric, the magnetic field doesn't depend on phi. It's the same no matter what angle you look at. So our magnetic field, which was a function of r, phi, and z, becomes just a function of r and z. Then our Lagrangian, which was 1/2 phi squared plus q, a at r and z dot v, also doesn't depend on phi. There's no phi that shows up. And so that means that Lagrangian has a symmetry. As you rotate in phi, nothing happens. A symmetry, through Noether's theorem, has to lead to a conserved quantity. Let's see how we get a conserved quantity out of our Lagrangian. Okay, so first things first, let's write our Lagrangian in cylindrical coordinates. We have r, phi, and z, and then we also have these variables r dot, phi dot, and z dot. These are not derivatives, they're just the sort of names I'm giving to the variables for the components of the velocity vector. Okay? And if we try to take the Euler-Lagrange equations in the phi variable, what we end up finding is that dl d phi dot, d by dt of that, has to be equal to dl d phi. So that's our Euler-Lagrange equations from before, but in this variable. But we know that L doesn't have a phi in it at all. So when you differentiate it in phi, it's independent of it, and the derivative is 0. What that tells us is that d by dt of dl d phi dot must be 0. So dl d phi dot must stay constant along a particle path. This is great, we've got a conserved quantity. But what does it actually mean? So we need to figure out what dl d phi dot is. Let's write out L in cylindrical coordinates. Remember that we had two terms, m over 2 times v squared. Okay, v squared is going to be r dot squared plus r squared phi dot squared plus z dot squared. This extra r squared comes from the fact that in cylindrical coordinates, we need to go from phi dot to r phi dot in order to get the distance as you move in the angular direction. This is related to angular velocity. Okay, and then we also had q times a dot with v. So we have AR, A phi, and AC. Those are the components in R phi and Z of A. And we need to dot with R dot, phi dot, Z dot. A of R times R dot and A of Z times Z dot makes sense. This middle term's a little weird. A phi, R phi dot. Again, this comes from the fact that in cylindrical coordinates, distances in the phi dot direction are actually R phi dot. As you move further away, when you sweep out an angle, you cover more area. Okay, and now we can compute the derivative with respect to phi dot. There's only two terms that depend on phi dot here. There's m over 2 r squared phi dot squared, and there's q a phi r phi dot. When you differentiate the first one with respect to phi dot, you get 2 times m over 2 times r squared phi dot. So that leads us to m r squared phi dot right here. The second term is q a phi r phi dot. In this case, it's linear in phi dot, so the phi dot just goes away, and we get q a phi r. This quantity, we know, must be conserved along the particle path, because d by dt of it is 0. So this is our conserved quantity from Noether's theorem. But as it turns out, this quantity is kind of hard to understand. First things first, we're going to have to compare the sizes of these two terms. Then we'll be almost done. How do we compare the sizes of these two terms? Let's divide them. M r squared phi dot divided by q a phi r. Now, r phi dot is about the velocity of the particle. A phi was an integral of b, so that means that it's about the size b times r. Okay. So substituting those in, we can split these up, and we end up getting two different terms. One is v over r, and one is m over qb. Well, v over r, this is the frequency. V is the speed of the particle, r is the size of the device. So v over r is the frequency at which the particle orbits around the device. In other words, it's the frequency at which the particle sees changes in the larger magnetic field. So we call that guy omega b. Meanwhile, b times q over m, this is actually the gyro frequency. This is how quickly the particle is spinning in its little gyro orbits around the magnetic field lines. And we know that as we pump the magnetic field up to be really, really strong, that the particle is spinning around those magnetic field lines, curling around the gyro orbits a lot faster than it's going around the larger device. So this omega b in the bottom is much, much bigger than the little omega b in the top. Which means that at the start, our m r squared phi dot term was much smaller than our q a phi r term in our conserved quantity. Okay, so I'm not going to ignore m r squared phi dot, but what I'm going to say is that it contributes an error. Let's see what that error is. The particles are going to stay contained to the constant surfaces, the level sets, of a phi times r. They will have a small error, but that error is going to be on the scale of the gyro motion. So the particles may escape these level sets just a little bit, but they can only go so far away as guaranteed by the fact that they're gyroing around the magnetic field lines. Then they'll come right back. So we know that there's this little bit of error from mr squared phi dot, but for the most part the particles are staying conserved to these level surfaces. And this is a really good thing, because it turns out that a phi r is a really nice function for its level surfaces. It's because a phi r is something called a flux function. A flux function is just like our psi from our Boozer coordinates. It's a function that labels the flux surfaces. What does this mean? It means that if a phi r is constant on a surface, that surface must be a flux surface. It must be a surface where the magnetic field lines lie. Let's see why. We're going to take the directional derivative of the magnetic field, or we're going to take the directional derivative of a phi r in the direction of the magnetic field. Okay, to do this, we're going to have to take the dot product of B with the gradient of a phi r. Because nothing depends on phi, the phi term goes away, and we just have br times d a phi r dr plus bz times d a phi r dz. R doesn't depend on z, so it can be pulled out. We also need to figure out what br and bz are. Because b was equal to the curl of a, br is minus d a phi by dz, and bz is 1 over r dr a phi dr. This is the curl in cylindrical coordinates. And we can substitute these in. R and 1 over r cancel, and the remaining terms are actually the same thing. So we get 0. What this means is that a phi r actually follows it, or is constant as it follows the magnetic field lines. So particle trajectories are confined to the flux surfaces where our magnetic field lines lie. Well, there's a little bit of error, but that error just comes from the gyro motion. Unfortunately, when we lose axis symmetry, this whole argument fails. We lose the conservation of a phi r, and we aren't able to guarantee that particle trajectories actually lie on the flux surfaces. So we need to do something to get things back. This is where quasisymmetry comes in. Quasisymmetry is the definition that's just enough for us to recover the flux surface conservation that we just derived via Noether's theorem. So again, that proof gets a little more complicated than this one, but it's also, sort of a similar idea. We go through Noether's theorem with Lagrangian, apply quasisymmetry, and we end up finding that the flux surface is conserved. Okay, so this is what I wanted to say about particle containment in the axisymmetric case. Again, this is kind of a tricky proof. It has a lot of moving parts, but if you've never seen Lagrangian mechanics before, now you know some of the kinds of things that we study when we study the Lagrangian. Okay, we're almost done, but before we finish, I just want to do a quick taste of differential geometry. Let's talk a little bit about differential forms and how they're related to quasisymmetric accelerators. So a magnetic field gives us 3 different differential forms that are important. The magnetic field itself is a vector field, but it also gives us a 1 form called the magnetic circulation, B dot dl. What does this guy do? It takes a vector u and it spits out B of x dot u. We also get a 2 form called the magnetic flux, B dot ds. This guy, if you feed in vectors u and v, it spits out B of x dot u cross v. And finally, okay, this one's cheating a little bit. It's a 0 form, so it's just a function. The magnetic strength, magnitude of B squared. Okay, so maybe you could call this a 3 form and think about it as the density in a volume, but we'll just think of it as a 0 form here. What can we do with differential forms? It seems kind of silly to take this vector field and turn it into all these differential forms. What's the value? One thing that we can do with differential forms is we can study symmetries of them. If you give me a vector field u, and you give me a differential form or a vector field, omega, then we call u an infinitesimal symmetry of omega, if the Lie derivative of omega with respect to u is 0. Okay, the Lie derivative is a pretty fancy concept, but the basic idea is u is a vector field which has a flow. It generates a flow, directions you should move in, and we just want to know if omega is changing as you move along the flow. If it's not, then u is called an infinitesimal symmetry of omega. So let's see what happens when we study infinitesimal symmetries of our magnetic field. U is an infinitesimal symmetry of the vector field B when u dot grad B minus B dot grad U is 0. U is an infinitesimal symmetry of the one form, B dot dl, if curl of B cross U plus grad of U dot B is 0. This is totally different. We have a new notion of symmetry when we go from thinking of B as a vector field to thinking of B as a one form. Now let's think of B as a two form. Now the notion of symmetry is curl of U cross B equals 0. Yet another new notion of symmetry. And finally, the notion of symmetry for our magnetic strength, magnitude of B squared. This one's a little simpler. It's just U dot grad B equals 0. It just says that B's magnitude doesn't change as you move along U. Okay, so we've got 4 different notions of symmetry for B now. Which of these is quasi-symmetry? It turns out it's not just one of them. It's 3 of them all at once. So quasi-symmetry is actually a lot more symmetric than just typical symmetry. So we say that U is a quasi-symmetry of B if it is an infinitesimal symmetry for all 3 of B dot dl, B dot ds, and magnitude of B squared at the same time. Okay, so we can have a vector field which is a quasi-symmetry of B, and the theorem, which is actually pretty recent from 2019, proved by Burby, Kalinikos, and Mackey, is that B is classically quasi-symmetric. That's quasi-symmetric in the sense of the Boozer plot that we talked about earlier, if and only if there is some non-trivial vector field U so that B is U quasi-symmetric in the sense defined above. This theorem is not easy to prove. They have to construct U in a very nasty way. Here you can see that U depends on B and psi, but also it depends on the C, which depends on U itself. So U is implicitly defined. You need to prove that a solution to these equations exists, and that once it does exist, that it satisfies all the different infinitesimal symmetries. So this is what we study when we study differential forms for plasmas. This is kind of a burgeoning field, but some of my colleagues here at NYU are trying to figure out how to use these differential forms to even do calculations and simulations on the computer. It's a really nice idea, and if you're interested in differential forms or differential geometry, I really recommend checking this out. The geometry of stellarators and of plasmas is really beautiful. Okay, so that is my talk. Thank you so much for attending. Here are some further resources. The textbook that I used to introduce myself to this topic was An Introduction to Stellarators by Elizabeth Paul, who's at Columbia. It's an excellent textbook and it's free on archive. There's the Quasar Stellarator Database, which is a cool exploration tool for seeing all kinds of different quasi-symmetric stellarators and how they look, and comparing them as a big data set on different axes. SimsOpt is the standard stellarator optimization suite. It works in Python, so give it a try. And I'm going to be doing a weekly problem thread this week in the Math Discord for studying all different kinds of ideas about math for fusion. So we'll continue talking about the mathematical ideas discussed here, and anything that people want me to go more in depth about, I can do little lectures written, or I guess I can also talk about those ideas a little bit more informally. Thank you again for attending. I'm putting up the crazy different stellarator pictures here so you can take a look at them again. I will stick around after this to answer people's questions about whatever they are curious about, whether it's plasma physics, stellarators, what the challenges are for doing nuclear fusion, and so on. But thank you again so much for attending, and I hope you enjoyed the talk.